Okay, let's have a look at certainty of measurement and significant figures. I've drawn what could be any apparatus here that's used to measure something. It could be measuring temperature, it could be measuring volume with a measuring cylinder. On the left hand side we've got a scale that gives us 11, so presumably higher we would have a 12 and underneath we would have a 10. And we've also got a decimal scale here going from 0.1, 0.2 up to 0.7. Now we've got 4 students who've taken a measurement with this particular apparatus. Student number 1 said 11.33, number 2 said 11.34, etc. down to 11.36 for the 4th student. So what can we say about this particular measurement? Well, first of all students agreed that we had 11 in here. So looking at our apparatus, and we'll assume that our apparatus was correctly made and therefore our measurement is accurate and precise, we can say that we're certain about the 11. We can also say from our measurements, and if we look at it here, that we've also got somewhere between 0.3 and 0.4. The important point there is that we can all agree that it's 0.3 something. So we're also certain about the 3rd digit there. However, if we look at the 4th digit, we've got a 0.03 to a 0.06. The students don't agree on that particular measurement. In other words, we have uncertainty about that 4th digit. And in a similar way, if we wrote down 11.355, we would be uncertain not only about the second last digit, but about the last digit as well. So what does that mean for us in terms of our measurement? Well, scientific numbers or measurements are represented so that every digit is certain except the last one. So in other words, we're certain about 1st, 2nd, 3rd here, but we're not certain about the last one. In other words, we have our first 3 which we're certain about, our last one we're uncertain about, and it's what we call an estimated value. We don't know, because our machinery isn't precise enough, to say whether it's 0.03, 0.04, 0.5 or 0.6. In other words, we're only as precise as our least accurate measuring scale. So what significance does this have for us when we do calculations and represent answers from those calculations? In order to look at this, we need to have an understanding of significant figures or significant digits. So from our previous measurements, we had a number of 11.35. We'll take it as that. Let's analyse that number for how significant, the number of figures we can represent this with. Our first rule says that non-zero digits are significant. So if we've got this particular number, all of those digits are significant for us because they're non-zeros. Exact numbers or defying numbers are always significant as well, and they have no uncertainty. So we have 100 centimetres in a metre, so that 100, that 100 will always have 3 significant figures. Our problems usually occur, in fact always occur, when we look at zeros being significant, whether they be decimal places or very large numbers. So we've got to set up some rules to determine how we represent those numbers in terms of their significant figures. So let's have a look at some. Zeros are significant when the 0 is represented between non-zero numbers. So we have a number here, 205. Our 0 is between the 2 non-zeros, therefore it's going to be significant. So in this particular example, we have 3 significant figures, and if we did a calculation involving this number, we would need to take into account this particular set of significant figures for our final answer. Now we can also say zeros are significant when they're at the end of a number, including decimals. And the reason we say that is because sometimes the precision of our instrument determines that. So in this particular example, we've weighed, let's say we've weighed something out to be 0.0500 kilograms. That's a precise measurement, and it has 3 significant figures. However, if I just included extra zeros on there, because I felt like it, those extra zeros would not be significant because we can't measure down any further than this with our piece of equipment. Our zeros are not significant when before the first non-zero, it's not significant when our zero is before the first non-zero. In other words, it's locating a decimal point. So we have this number 0.0025. We've just said from our rule, zeros before the first non-zero are not significant. So for this particular measurement, we have two significant figures. And lastly, if we have a number with a zero after another number without a decimal point, those zeros are not significant either. So in this particular example with our 1,000, we have the first one significant, the last three are not significant. On the other hand, if we had a 0.0 there, then that would be significant. So how do we use these rules to determine significant figures in measurement and calculations? The number 87,000. Well, if we look at our rules, any zeros that trail non-zeros are not significant. So in this particular example, we have two significant figures. In the second example, we have something similar, but we've added another layer of complexity. So we have 3 zeros at the end. They're not significant because that's similar to the first one. But this particular zero is significant because it lies between two non-zeros. So for this one, we have three significant figures. For the next example, 4.0005, all of our zeros sit between non-zeros. So all the zeros here are significant, therefore we have 5 significant figures. In our fourth example, we have the number 4.000. The zeros are represented here as a measure of the precision of our measuring instrument, therefore they are significant. So we have 4 significant figures in this particular example. And our last one, 0.000503, we said that zeros before a decimal place were not significant. Before our first non-zero with a decimal place were not significant. Therefore, we have the 5, the 0, similarly to the second example, and the 3. So we have 3 significant figures for that particular one. Now, this has ramifications when we round in calculations.